All right, let's just go over a quick geometric example of how to use similar matrices. Suppose we have a transformation T that takes the vector 1, 1, and it's going to stretch it by a factor of 4 to 4, 4. And it's going to take 1 minus 1, and it's going to stretch it by a factor of 2 to 2 minus 2. And so the goal is to calculate the matrix for T. All right, so why do we care about the matrix for T? Well, right now we only know what T does for 1, 1 and 1 minus 1. But what we want to be able to do is to do this for any particular vector, say 5, 0. And if we know that matrix, it's just that matrix times the vector. So calculating the specific matrix will define this transformation for any possible vector. And turns out we have just enough information to do that, but it's not obvious exactly what the matrix is. And we're going to use similar matrices to get this. The main idea of what we're going to do is we're going to transform the standard basis into the basis of the vectors we were given. So we know what happens specifically to these two vectors. And because of that, we're going to transform into a basis of those two vectors. And then we're going to apply T. And then we're going to move it back. And so we can describe T as just shortcutting all three of these steps. So if this final step is S, this middle step is D, and this first step is going to be S inverse, then altogether our transformation T is the same thing as doing those three things. So we can write it like this. Keep in mind that we write it in the reverse direction that we perform them in, because matrix multiplication is written right to left based upon the order that you perform them in. Right? So because we're going to perform S inverse first, then D, then S, we're going to write S inverse on the right side, then D, and then S on the far left. And so if we can figure out what these three individual pieces are, we'll be able to find what D is. Now, each of these pieces is actually more straightforward than it looks. So let's start with the right. The right here, this is just changing from the weird basis to a standard basis. So the matrix is just the amalgamated matrix. So why is that? Well, if we express a vector as a combination of those two weird vectors, this is the same thing as 1, 1, 1 minus 1 times the vector AB. And so hence the change of basis is just that matrix 1, 1, 1 minus 1. And that's going to be true of any time you convert from a weird basis into a standard basis. And similarly, we know that S inverse, it's just going to be the inverse to this matrix. And so we can use our formula. Where this formula comes from is going to be much more clear later. But we'll end up getting a very similar looking matrix, but just with the ones replaced by halves. So now we know S and we know S inverse. So the only thing that's left to calculate is what this D is. And this D is where the geometry and the intuition comes into play, because we know specifically what's going to happen to these two vectors. We know that 1, 1 stretches by a factor of 4. So in this very specific direction, 1, 1, it's going to stretch by a factor of 4. And it does nothing else. It has nothing to do with the other vector. It just stretches by 4. And similarly, the other vector is going to stretch by a factor of 2. So because this is just stretching in 2 particular directions, it's encoded by a diagonal matrix where the factors of stretches are just on the diagonal. And so now we have the 3 pieces. We have S, we have S inverse, and we have D. So we now know what T is. So T altogether is just S, D, S inverse, which is equal to 1/2, 1/2, 1/2, minus 1/2 times 4002 times 111 minus 1. And this may seem like magic, but I just want to reiterate, what we're doing is we're transforming the basis into the information we know, and then stretching it, and then pushing it back. So this is transforming it. No, I made a mistake here. These are actually in the reverse order. Right, that's S inverse. That's S. Let's put that over there. There we go. Made a slight mistake. So we're going to change the basis, stretch, change back. So that's what's going on here. And so this is actually a very powerful idea and the power behind similar matrices. All right, so let's multiply all this out and see what happens. So let's do these 2 first. So this one's going to be 4, 2, that's a 4, and it's a minus 2. All right. And we can do the same thing again. It may seem a little tedious, but let's just keep going. So that's 3 right there. That's a 1. That one's also a 1. I think this last one will be a 3. Let's just check it out. That's going to be a 3. All right. So that's our matrix T. So we're able to find the exact matrix for the transformation defined by just these 2 specific points. We were able to find the matrix for any point. Let's check this. So we're gonna do a check. So if this works out, T of 1, 1 better be 4, 4. And sure enough, that's what happens. And likewise, if we do T of 1 minus 1, we better get 2 minus 2. And sure enough, if we do that, that also checks out as well. So this is the specific matrix that we did. And what we did to do this was we just changed the basis, applied the transformation, and changed back. And that's kind of the power of similar matrices.